Section 1.6, Properties of Integral Exponents. In this section, we're going to be taking a closer look at exponents and what we mean by that terminology. This is expanding our set of operations that we can perform on numbers and variables. We've talked about addition, subtraction, multiplication, and division. Another common and useful operation is something called exponentiation, or using exponents. And it really can be generalized in one way of thinking of the same way that we generalized addition into multiplication. We said that multiplication could be thought of as repeated addition. Okay, that's not the only thing that it is, but in most cases that's a pretty good description of multiplication, is repeated addition. Well, if we do repeated multiplication, that's what we're going to refer to as exponentiation, or exponents. And how we write that and how we how we simplify that operation is what we're going to be covering in this section. Our outline for this section, including the essential concepts, are the following. We're going to look at 7 rules for exponents. We're going to derive them and learn how to use them. These include the product rule, the quotient rule, the zero exponent, the negative exponent, the power to a power, the power of a product, and the power of a quotient. Then once we know those 7 rules, which you'll be actually asked to know from memory, we are going to then simplify expressions that involve exponents. Let us begin by looking at the first 2 of the 7 rules, 2 that are very similar to each other, what are called the product and the quotient rules. The product rule says the following: when multiplying exponential expressions with the same base, we add the exponents. So the rule looks like this. If you have b to the m times b to the n, that is b to the m plus n. We add the exponents. Now, why does that make sense? Well, think about it this way. If I had b to the 4th times b to the 3rd, recall from before that raising something to a power simply means multiply it times itself that many times. So b to the 4th is b times b times b times b. Right? And we're going to multiply that times b cubed, right? Which is b times b times b. Now, how many b's do I have multiplied together now? Right? It's the 4 from before and the 3 after. So I'm going to take 4 plus 3 and have b to the 7th, which is 4 plus 3. So multiplying exponential expressions with the same base means to add their exponents. Alright, so consider this example. What do we get when we multiply b to the 8th times b to the 10th? Okay, according to the product rule, that would be b to the 18th, and that's all you have to do there. Okay. Now, what happens if we have several exponents and all multiplied together? Notice the operation that's assumed in between these 2 parentheses is multiplication, so everything here is multiplied. There's no addition inside the problem, it's all multiplication. So what you can do, because of the associativity rule and the commutativity rules for multiplication, you can put the numbers together, the x's together, and the y's together. Right? You could say this is the same thing as 4 times 10, x cubed times x squared, and y to the 4th times y to the 6th. Now, I don't ask you to write this out every single time, but this is just so you see what I'm actually doing when I put the numbers multiplied together. 4 times 10 is 40. X to the 3rd times x squared would be x to the 3 plus 2, which is x to the 5th. Right? And then y to the 4th times y to the 6th. You add the exponents, you get y to the 10th, and so that is your simplified expression. The second rule is the quotient rule, which says when dividing exponential expressions with the same non-zero base, we subtract the exponent in the denominator from the exponent in the numerator, or equivalently, we subtract the smaller exponent from the larger exponent and put the answer on the end of the fraction with the larger exponent. So as you can see here, it may very well be that you have b to the m over b to the n would be b to the m minus n, or you get the same answer if you take n minus m and put it on bottom. So whichever one you subtract from, that's the end of the fraction that you stay on, right? So this m was first, this here, the n was first. That just allows us to not have to deal with negative exponents yet. Alright, we can just subtract the larger minus the smaller. Now let's just think for a second why that makes sense. Go back to a particular numerical example. We have b to the 7th, which would be b times b times b times b times b times b times b. That's 7 b's divided by b to the 3rd, which is b times b times b. Okay. Now why do I subtract? Well, think about it this way. B over b, this b over b here, right, I could pull off to the side. That's simply going to divide out and leave me with 1, right? B over b is 1. This b and this b similarly cancel. This b and this b cancel because we're dividing out things that are multiplied on. What am I left with? I'm left with b to the 4th. Now why is that subtraction? Well, think about it. I started with 7 and I took away the 3 that were on bottom. So that was 7 minus 3, or b to the 4th. Right? So you can see pretty quickly how these would work. If I have b to the 15th over b to the 3rd, I have more b's on top. So I'm going to end up with b to the 15 minus 3, or 12. I could write it on top like this, but anything over 1 is itself, so it would just be b to the 12th. Right? If you cancel everything out of the denominator, what you're left with is a 1, because you've divided it out, and when you divide something out, you're left with 1. What about if you had b to the 3rd over b to the 15th? Now, I'm going to take away 3, but I have more on bottom, so that's where I'm still going to have 12 of these b's left. 15 minus 3 is 12, but they're on bottom now, and since everything's gone on top, I do have to write the 1, right? 1 divided by b over 12, or b to the 12th. And we can also have a combination of a problem here where we've got multiple terms. In this case, I would have 27 divided by 3 gives me a 9 on top. X to the 14th divided by x to the 3rd gives me x to the 11th on top. Y to the 8th over y to the 5th gives me y to the 3rd on top, because 8 minus 5 is 3, all over 1, or 9x to the 11th y to the 3rd is my final answer. The next rule is the zero exponent rule. It says that if b is any real number besides 0, then b to the 0 is always 1. Anything raised to the 0 power is equal to 1. Now why is that true? Well, think about it. If I took b to the 4th over b to the 4th, okay, clearly that's 1, right? Because we know anything divided by itself is 1. But by the quotient rule, we know it also has to be equal to b to the top minus the bottom, exponents, 4 minus 4, which is b to the 0. So this has to equal 1 because we know anything divided by itself is equal to 1. So for the quotient rule to be consistent, that has to be the case. We know b to the 4th over b to the 4th is b to the 4 minus 4. We also know b to the 4th divided by b to the 4th is 1. So that means that's always true. Anything to the 0 power is equal to 1. So here's some easy questions down here to answer. What's 8 to the 0? 1. What's negative 5 to the 0? 1. What's 10x to the 0? Now note, that is not the same thing as this. Right? 10x all to the 0 would be 1. But what do your order of operations tell you to do first? Parentheses, then exponents, right? So you first do this. X to the 0 is 1, and then you multiply. So actually, try to throw you a curveball there, but pay attention. 10x to the 0 is actually 10. Okay? Now, this should be a typo. Mark this out on D and write this. Write 10x all raised to the 0 power. That's the problem I intended to put on D. That is 1. And notice I even threw you a curveball here, or at least I tried to. I think it should be obvious no matter what I put inside here. Even if I have a complicated mathematical expression that looks like this, anything raised to the 0 power is 1. Okay, that's the 0 exponent rule. Anything to the 0 power is 1. The negative exponent rule. It says that if b is any number other than 0 and n is a natural number, then raising b to a negative number is the same thing as dividing 1 by b to that positive number. B to the minus n is 1 over b to the n. Note also 1 over b to the minus n is the same thing as b to the n over 1, or just b to the n. So negative exponents mean, I'll put a double arrow here for, is the same thing as move to other end of fraction. Okay, so if it's b to the minus n, like b to the minus n would be the same thing as b to the minus n over 1. You take the b to the minus n and you move it down, it becomes b to the positive n. If your b to the minus n was on bottom, you moved it up to the top. Okay, so 5 to the minus 2 is 1 over 5 to the positive 2, or 1/25. Note, it's easy to see this, but it's not negative 25. Okay? All right, that is the wrong answer. Just because there's a negative in the exponent doesn't mean the same thing as negative out front. It's a very important principle to recognize when you're dealing with exponents. Negatives in exponents don't mean the same thing as negatives out front. What it means is divide by that exponent. 3x to the minus 6y to the 4th. Okay? If you treat this as a fraction, as all over 1, you're going to take the thing that has the negative exponent and move it to the bottom of the fraction. So this becomes 3y to the 4th over x to the positive 6. And that's the simplified expression using the negative exponent rule. Similarly, on this one, I can take the 7 to the minus 2. I'm going to move it down. I'm going to take x to the minus 3. I'm going to move it up. And what I end up with is x to the positive 3 on top divided by a 7 squared and a 4. Now anytime you have numbers raised to powers, you can go ahead and simplify those. So this becomes x cubed over 49 times 4. Okay, 49 is what 7 squared is. 49 times 4 is, let's see, 6k or 3, so 196 on bottom. There is your simplified expression. Negative exponent rule. Alright, stay with me here. We've got 3 more rules now. We've done 4 rules, we've got 3 more. Power to powers. When an exponential expression is raised to a power, we multiply the exponents. And then you place the product of the exponents on the base and remove the parentheses. So here's what we've got. B to the m times n is b to the m times, sorry, I should say that better. B to the m all raised to the nth power is b to the m times n. Now, if you think about it, this also makes sense. Just recognize what we mean by raising something to a power. B squared inside is b times b, right? Now what if I multiply that times itself 4 times? The parentheses are just other ways of writing multiplication, right? So I can get rid of these parentheses if I'm careful. Oh, I accidentally erased one of my b's, didn't I? Put that b back. Alright, and this guy. So now we've just got them all multiplied together. How many b's do we have? We have 8 of them, right? 2 times 4 is 8. So let's use that rule to simplify this. X to the 5th cubed would be x to the 15th, and that's it. Y to the 7th raised to the negative 2 would be y to the 7 times negative 2, or negative 14, which by the previous rule is 1 over y to the positive 14. Note, the answer is not simplified until all exponents are positive. So if I stopped here, I would not be all the way finished simplifying, right? I still have a little bit more work to do. The last two rules are similar. We have the products to powers rule and the quotients to powers rule. Here's what it says when we talk about the products to powers. When a product is raised to a power, raise each factor to that power. A times b all raised to the nth is the same thing as a to the n, b to the n. Okay, and that's not hard to see. Just think about this. 2x to the 4th is 2x times 2x times 2x times 2x, right? Which is 2 to the 4th, because we got 4 2's, and x to the 4th, because we got 4 x's, okay, or 16x to the 4th. So I could have just taken 4 and raised each thing inside to the 4th. Now it's tempting to forget to do the 2, but you got to do it all. So take this for example. Negative 3y squared to the 3rd. That's going to be negative 3 to the 3rd, and then y squared to the 3rd, or negative 27y to the 6th. Because when we raise power to power, we multiply. Okay? Now on b, if we use the power to power rule, we'll have negative 4 to the minus 2, x to the 5th to the minus 2, and y to the minus 1 to the minus 2. Okay? So that's negative 4 to the minus 2, x to the minus 10, y to the positive 2. I'm multiplying power raised to a power. Now in this case, because I've got negative exponents, I've got to move them to the other end of the fraction. Here's what I do. I write it over 1, and I take anything that has a negative exponent and I move it. So I end up with y squared on top, negative 4 squared, and x to the positive 10. Now negative 4 squared is 16, so I can go ahead and multiply it out whenever it's a number. 16 x to the 10th. And that's what I get when it's completely simplified. So I distributed the minus 2 to every factor inside, and then I applied my other rules to help finish the simplification process. Quotients to a power work exactly like products to a power. When a quotient is raised to a power, you're going to raise the numerator, sometimes called the dividend, to that power, and raise the denominator, or the quotient, to that power as well. A over b raised to the nth is a to the nth over b to the nth. Right? So this example, x to the 5th over 4 all cubed would be x to the 5th cubed over 4 cubed, or x to the 15th over 64. The next example here, similarly, I will take x cubed and raise it to the negative 4 divided by y squared raised to the negative 4, which gives me x to the negative 12 over y to the negative 8. Because they have negative exponents, I'm going to have to move them, which leaves me with y to the positive 8 on top and x to the positive 12 on bottom. Now, just in summary of our 7 rules, we've talked about the power rule, the quotient rule, the zero exponent, the negative exponent, the power to a power, and then products and quotients to power rules. It's possible to have several of these rules need to be applied in a single example, a single expression. And so here are some guidelines so that you have an idea of when the expression is completely simplified. Okay, you know it's simplified if, one, no parentheses appear. If you have completely distributed all the exponents from the power to power or products and quotients to powers. You also need to have that no other powers are raised to any others. No powers are raised to powers. H base occurs only once, meaning that you cannot combine bases with the product rule or the quotient rule. And no negative or zero exponents appear. So let's look at this example here. We have negative 3x to the minus 6 times negative 2x cubed y to the fourth squared. Now, because this is an exponent on the second factor, the second set of parentheses, it applies only to those parentheses. So I need to do that first because exponents come before multiplication. So I'll have minus 3x to the minus 6y times a negative 2 squared, an x cubed squared, and a y to the fourth squared. Okay? So let's see what we got. Let's raise the ones that we can do. So we have negative 3 x to the minus 6th y. Negative 2 squared is times 4. X to the third to the second is x to the 6th. Y to the fourth squared is y to the 8th. Now we're going to put each factors together. Negative 3 times 4 is negative 12. We have x to the 6th and x to the minus 6th. We add those exponents. We have y to the first and y to the 8th, so we add those. I end up with negative 12 x to the 0, y to the 9th, because negative 6 plus 6 is 0, which is negative 12y to the 9th. Let's take a look at the next one. We have now a fraction, so I'm going to raise both the numerator and denominator to this power. I'll have x to the third, y to the fifth as the numerator, raised to the negative third, over 4 raised to the negative third. So we have x to the third. Because this is a product now, I can actually raise each of these factors to the minus 3. And that's still 4 to the minus 3 in the denominator. So that's x to the minus 9, y to the minus 15 over 4 to the minus 3. So everything's going to move to the other end. I'll have x to the, 4 to the minus 3 comes at the top. I'll have 4 to the positive 3. X to the minus 9 comes to the bottom. I have x to the 9th. Y to the minus 15th comes to the bottom. I have y to the 15th. So that's 64 over x to the 9th, y to the 15th. Okay? By the way, I apologize. At the bottom of your page there, you have a homework set due line. That's from the version of the homework that was, version of the lecture notes were distributed in my traditional classes. You could ignore that. Pay attention to the assignments in Blackboard and Course Compass for your correct due dates. That ends section 1.6 and our work with exponential expressions.